Yes, welcome back. Let's read this.
Air traffic control. Air traffic redirects here. For the Canadian band, see Air traffic control band. For the Owl City song, see Maybe I'm Dreaming. This article is about civilian direction of aircraft. For other types of aircraft control, see Air control. This article has multiple issues. Please help improve it or discuss these issues on the talk page. Learn how and when to remove these template messages. This article possibly contains original research. April 2019. This article needs additional citations for verification. April 2019. Air Traffic Control, ATC, is a service provided by ground-based air traffic controllers who direct aircraft on the ground and through a given section of controlled airspace, and can provide advisory services to aircraft in non-controlled airspace. The primary purpose of ATC worldwide is to prevent collisions, organize and expedite the flow of air traffic, and provide information and other support for pilots. Air traffic controllers monitor the location of aircraft in their assigned airspace by radar and communicate with the pilots by radio. To prevent collisions, ATC enforces traffic separation rules, which ensure each aircraft maintains a minimum amount of empty space around it at all times. It is also common for ATC to provide services to all private, military, and commercial aircraft operating within its airspace, not just civilian aircraft. Depending on the type of flight and the class of airspace, ATC may issue instructions that pilots are required to obey, or advisories, known as flight information in some countries, that pilots may, at their discretion, disregard. The pilot in command is the final authority for the safe operation of the aircraft and may, in an emergency, deviate from ATC instructions to the extent required to maintain safe operation of their aircraft. Language, edit. See also, Aeronautical Phraseology and Aviation English. Pursuant to requirements of the International Civil Aviation Organization, ICAO, ATC operations are conducted either in the English language or the language used by the station on the ground. In practice, the native language for a region is used, however, English must be used upon request. History, edit. In 1920, Croydon Airport, London, was the first airport in the world to introduce air traffic control. The Aerodrome Control Tower was a wooden hut 15 feet, 4.6 m, high with windows on all four sides. It was commissioned on the 25th of February 1920 and provided basic traffic, weather and location information to pilots. In the United States, air traffic control developed three divisions. The first of several airmail radio stations, AMRS, was created in 1922 after World War I when the U.S. Post Office began using techniques developed by the Army to direct and track the movements of reconnaissance aircraft. Over time, the AMRS morphed into flight service stations. Today's flight service stations do not issue control instructions, but provide pilots with many other flight-related informational services. They do relay control instructions from ATC in areas where flight service is the only facility with radio or phone coverage. The first airport traffic control tower, regulating arrivals, departures and surface movement of aircraft at a specific airport, opened in Cleveland in 1930. Approach forward/departure control facilities were created after adoption of radar in the 1950s to monitor and control the busy airspace around larger airports. The first Air Route Traffic Control Center, ARTC, which directs the movement of aircraft between departure and destination, was opened in Newark in 1935. followed in 1936 by Chicago and Cleveland. Currently in the U.S., the Federal Aviation Administration, FAA, operates 22 ATCs. After the 1956 Grand Canyon mid-air collision, killing all 128 on board, the FAA was given the air traffic responsibility over the United States in 1958, and this was followed by other countries. In 1960, Britain, France, Germany and the Benelux countries set up Eurocontrol, intending to merge their airspaces. The first and only attempt to pool controllers between countries is the Maastricht Upper Area Control Center, MAC, founded in 1972 by Eurocontrol and covering Belgium, Luxembourg, the Netherlands and northwestern Germany. In 2001, the EU aimed to create a single European sky, hoping to boost efficiency and gain economies of scale. Airport Traffic Control Tower, EDIT. The primary method of controlling the immediate airport environment is visual observation from the airport control tower. The tower is a tall, windowed structure located on the airport grounds. Air traffic controllers are responsible for the separation and efficient movement of aircraft and vehicles operating on the taxiways and runways of the airport itself, and aircraft in the air near the airport, generally 5 to 10 nautical miles, 9 to 18 kilometers, depending on the airport procedures. A controller must carry out the job using the precise and effective application of rules and procedures. However, they need flexible adjustments according to differing circumstances, often under time pressure. In a study that compared stress in the general population and this kind of system markedly showed more stress level for controllers. This variation can be explained, at least in part, by the characteristics of the job. Surveillance displays are also available to controllers at larger airports to assist with controlling air traffic. Controllers may use a radar system called secondary surveillance radar for airborne traffic approaching and departing. These displays include a map of the area, the position of various aircraft, and data tags that include aircraft identification, speed, altitude, and other information described in local procedures. In adverse weather conditions, the tower controllers may also use Surface Movement Radar, SMR, Surface Movement Guidance and Control System, SMGCS, or Advanced Surface Movement Guidance and Control System, ASUMGS, to control traffic on the maneuvering area, taxiways and runway. The areas of responsibility for tower controllers fall into 3 general operational disciplines: local control or air control, ground control, and flight data forward/clearance delivery. Other categories, such as airport apron control or ground movement planner, may exist at extremely busy airports. While each tower may have unique airport-specific procedures, such as multiple teams of controllers, crews, at major or complex airports with multiple runways, the following provides a general concept of the delegation of responsibilities within the tower environment. Remote and Virtual Tower, RVT, is a system based on air traffic controllers being located somewhere other than at the local airport tower and still able to provide air traffic control services. Displays for the air traffic controllers may be live video, synthetic images based on surveillance sensor data, or both. Ground Control, EDIT. Inside Pope Field Air Traffic Control Tower. Ground Control, sometimes known as Ground Movement Control, GMC, is responsible for the airport movement areas, as well as areas not released to the airlines or other users. This generally includes all taxiways, inactive runways, holding areas, and some transitional aprons or intersections where aircraft arrive, having vacated the runway or departure gate. Exact areas and control responsibilities are clearly defined in local documents and agreements at each airport. Any aircraft, vehicle, or person walking or working in these areas is required to have clearance from ground control. This is normally done via VHF/UHF radio, but there may be special cases where other procedures are used. Aircraft or vehicles without radios must respond to ATC instructions via aviation light signals or else be led by vehicles with radios. People working on the airport surface normally have a communications link through which they can communicate with ground control, commonly either by handheld radio or even cell phone. Ground control is vital to the smooth operation of the airport because this position impacts the sequencing of departure aircraft, affecting the safety and efficiency of the airport's operation. Some busier airports have surface movement radar, SMR, such as ASD-3, AMAS, or ASD-X, designed to display aircraft and vehicles on the ground. These are used by ground control as an additional tool to control ground traffic, particularly at night or in poor visibility. There is a wide range of capabilities on these systems as they are being modernized. Older systems will display a map of the airport and the target. Newer systems include the capability to display higher quality mapping, radar targets, data blocks, and safety alerts, and to interface with other systems such as digital flight strips. Air control or local control, edit. Air control, known to pilots as tower or tower control, is responsible for the active runway surfaces. Air control clears aircraft for takeoff or landing, ensuring that prescribed runway separation will exist at all times. If the air controller detects any unsafe conditions, a landing aircraft may be instructed to go around and be resequenced into the landing pattern. This resequencing will depend on the type of flight and may be handled by the air controller, approach, or terminal area controller. Within the tower, a highly disciplined communications process between the air control and ground control is an absolute necessity. Air control must ensure that ground control is aware of any operations that will impact the taxiways, and work with the approach radar controllers to create gaps in the arrival traffic to allow taxiing traffic to cross runways and to allow departing aircraft to take off. Ground control needs to keep the air controllers aware of the traffic flow towards their runways to maximize runway utilization through effective approach spacing. Crew resource management, CRM, procedures are often used to ensure this communication process is efficient and clear. Within ATC, it is usually known as TRM, Team Resource Management, and the level of focus on TRM varies within different ATC organizations. Flight data and clearance delivery, edit. Clearance delivery is the position that issues route clearances to aircraft, typically before they commence taxiing. These clearances contain details of the route that the aircraft is expected to fly after departure. Clearance delivery or, at busy airports, Ground Movement Planner, GMP, or Traffic Management Coordinator, TMC, will, if necessary, coordinate with the relevant radar center or flow control unit to obtain releases for aircraft. At busy airports, these releases are often automatic and are controlled by local agreements allowing free-flow departures. When weather or extremely high demand for a certain airport or airspace becomes a factor, there may be ground stops, or slot delays, or reroutes may be necessary to ensure the system does not get overloaded. The primary responsibility of clearance delivery is to ensure that the aircraft has the correct aerodrome information, such as weather and airport conditions, the correct route after departure, and time restrictions relating to that flight. This information is also coordinated with the relevant radar center or flow control unit and ground control to ensure that the aircraft reaches the runway in time to meet the time restriction provided by the relevant unit. At some airports, clearance delivery also plans aircraft pushbacks and engine starts, in which case it is known as the Ground Movement Planner, GMP. This position is particularly important at heavily congested airports to prevent taxiway and apron gridlock. Flight data, which is routinely combined with clearance delivery, is the position that is responsible for ensuring that both controllers and pilots have the most current information, pertinent weather changes, outages, airport ground delays, /ground stops, runway closures, etc. Flight data may inform the pilots using a recorded continuous loop on a specific frequency known as the Automatic Terminal Information Service, ATC. Approach and Terminal Control, edit. See also, Terminal Control Area. Trican redirects here. For the video game series, see Trican series. Many airports have a radar control facility that is associated with the airport. In most countries, this is referred to as terminal control and abbreviated to TMC. In the US, it is referred to as ATRICON, Terminal Radar Approach Control. While every airport varies, terminal controllers usually handle traffic in a 30 to 50 nautical mile, 56 to 93 kilometers, radius from the airport. Where there are many busy airports close together, one consolidated terminal control center may service all the airports. The airspace boundaries and altitudes assigned to a terminal control center, which vary widely from airport to airport, are based on factors such as traffic flows, neighboring airports and terrain. A large and complex example was the London Terminal Control Centre, which controlled traffic for 5 main London airports up to 20,000 feet, 6,100 m, and out to 100 nautical miles, 190 kilometers. Terminal controllers are responsible for providing all ATC services within their airspace. Traffic flow is broadly divided into departures, arrivals, and overflights. As aircraft move in and out of the terminal airspace, they are handed off to the next appropriate control facility, a control tower, an en route control facility, or a bordering terminal or approach control. Terminal control is responsible for ensuring that aircraft are at an appropriate altitude when they are handed off, and that aircraft arrive at a suitable rate for landing. Not all airports have a radar approach or terminal control available. In this case, the en route center or a neighboring terminal or approach control may coordinate directly with the tower on the airport and vector inbound aircraft to a position from where they can land visually. At some of these airports, the tower may provide a non-radar procedural approach service to arriving aircraft handed over from a radar unit before they are visual to land. Some units also have a dedicated approach unit which can provide the procedural approach service either all the time or for any periods of radar outage for any reason. In the US, TICONs are additionally designated by a 3-digit alphanumeric code. For example, the Chicago Trican is designated C90. Area Control Center / en route center, edit. Main article, Area Control Center. ATC provides services to aircraft in flight between airports as well. Pilots fly under one of two sets of rules for separation, Visual Flight Rules, VFR, or Instrument Flight Rules, IFR. Air traffic controllers have different responsibilities to aircraft operating under the different sets of rules. While IFR flights are under positive control, in the US and Canada VFR pilots can request flight following radar advisories, which provides traffic advisory services on a time-permitting basis and may also provide assistance in avoiding areas of weather and flight restrictions, as well as allowing pilots into the ATC system prior to the need to a clearance into certain airspace. Across Europe, pilots may request for a flight information service, which is similar to flight following. In the UK it is known as a basic service. En route air traffic controllers issue clearances and instructions for airborne aircraft, and pilots are required to comply with these instructions. En route controllers also provide air traffic control services to many smaller airports around the country, including clearance off of the ground and clearance for approach to an airport. Controllers adhere to a set of separation standards that define the minimum distance allowed between aircraft. These distances vary depending on the equipment and procedures used in providing ATC services. General characteristics, edit. En route air traffic controllers work in facilities called air traffic control centers, each of which is commonly referred to as a center. The United States uses the equivalent term Air Route Traffic Control Center. Each center is responsible for a given flight information region, FIR. Each flight information region covers many thousands of square miles of airspace and the airports within that airspace. Centers control IFR aircraft from the time they depart from an airport or terminal area's airspace to the time they arrive at another airport or terminal area's airspace. Centers may also pick up VFR aircraft that are already airborne and integrate them into the system. These aircraft must continue under VFR flight rules until the center provides a clearance. Center controllers are responsible for issuing instructions to pilots to climb their aircraft to their assigned altitude while, at the same time, ensuring that the aircraft is properly separated from all other aircraft in the immediate area. Additionally, the aircraft must be placed in a flow consistent with the aircraft's route of flight. This effort is complicated by crossing traffic, severe weather, special missions that require large airspace allocations, and traffic density. When the aircraft approaches its destination, the center is responsible for issuing instructions to pilots so that they will meet altitude restrictions by specific points, as well as providing many destination airports with a traffic flow, which prohibits all of the arrivals being bunched together. These flow restrictions often begin in the middle of the route, as controllers will position aircraft landing in the same destination so that when the aircraft are close to their destination they are sequenced. As an aircraft reaches the boundary of a center's control area, it is handed off or handed over to the next area control center. In some cases this handoff process involves a transfer of identification and details between controllers so that air traffic control services can be provided in a seamless manner. In other cases local agreements may allow silent handovers such that the receiving center does not require any coordination if traffic is presented in an agreed manner. After the handoff, the aircraft is given a frequency change and begins talking to the next controller. This process continues until the aircraft is handed off to a terminal controller. Approach. Radar coverage, edit. Since centers control a large airspace area, they will typically use long-range radar that has the capability, at higher altitudes, to see aircraft within 200 nautical miles, 370 kilometers, of the radar antenna. They may also use radar data to control when it provides a better picture of the traffic or when it can fill in a portion of the area not covered by the long-range radar. In the U.S. system, at higher altitudes, over 90% of the U.S. airspace is covered by radar and often by multiple radar systems. However, coverage may be inconsistent at lower altitudes used by aircraft due to high terrain or distance from radar facilities. A center may require numerous radar systems to cover the airspace assigned to them, and may also rely on pilot position reports from aircraft flying below the floor of radar coverage. This results in a large amount of data being available to the controller. To address this, automation systems have been designed that consolidate the radar data for the controller. This consolidation includes eliminating duplicate radar returns, ensuring the best radar for each geographical area is providing the data, and displaying the data in an effective format. Centers also exercise control over traffic traveling over the world's ocean areas. These areas are also Flight Information Regions, FIRs. Because there are no radar systems available for oceanic control, oceanic controllers provide ATC services using procedural control. These procedures use aircraft position reports, time, altitude, distance, and speed to ensure separation. Controllers record information on flight progress strips and in specially developed oceanic computer systems as aircraft report positions. This process requires that aircraft be separated by greater distances, which reduces the overall capacity for any given route. See for example the North Atlantic Track System. Some air navigation service providers, for example, Air Services Australia, the US Federal Aviation Administration, NAV Canada, etc., have implemented Automatic Dependent Surveillance Broadcast, ADS-B, as part of their surveillance capability. This new technology reverses the radar concept. Instead of radar finding a target by interrogating the transponder, the ADS-B-equipped aircraft sends a position report as determined by the navigation equipment on board the aircraft. ADS-C is another mode of automatic dependent surveillance. However, ADS-C operates in the contract mode where the aircraft reports a position, automatically or initiated by the pilot, based on a predetermined time interval. It is also possible for controllers to request more frequent reports to more quickly establish aircraft position for specific reasons. However, since the cost for each report is charged by the ADS service providers to the company operating the aircraft, more frequent reports are not commonly requested except in emergency situations. ADS-C is significant because it can be used where it is not possible to locate the infrastructure for a radar system, for example, over water. Computerized radar displays are now being designed to accept ADS-C inputs as part of the display. This technology is currently used in portions of the North Atlantic and the Pacific by a variety of states who share responsibility for the control of this airspace. Precision approach radars, PAR, are commonly used by military controllers of air forces of several countries, to assist the pilot in final phases of landing in places where instrument landing system and other sophisticated airborne equipment are unavailable to assist the pilots in marginal or near zero visibility conditions. This procedure is also called torque downs. A radar archive system, RAS, keeps an electronic record of all radar information, preserving it for a few weeks. This information can be useful for search and rescue. When an aircraft has disappeared from radar screens, a controller can review the last radar returns from the aircraft to determine its likely position. For example, see this crash report. RAS is also useful to technicians who are maintaining radar systems. Flight traffic mapping, edit. The mapping of flights in real time is based on the air traffic control system and volunteer ADS-B receivers. In 1991, data on the location of aircraft was made available by the Federal Aviation Administration to the airline industry. The National Business Aviation Association, NBAA, the General Aviation Manufacturers Association, the Aircraft Owners and Pilots Association, the Helicopter Association International, and the National Air Transportation Association petitioned the FAA to make ADS-D information available on a need-to-know basis. Subsequently, NBAA advocated the broad-scale dissemination of air traffic data. The Aircraft Situational Display to Industry, ADS-D, system now conveys up-to-date flight information to the airline industry and the public. Some companies that distribute ADS-D information are Flight Explorer, Flight View, and Flightcom. Each company maintains a website that provides free updated information to the public on flight status. Standalone programs are also available for displaying the geographic location of airborne IFR, instrument flight rules, air traffic anywhere in the FAA air traffic system. Positions are reported for both commercial and general aviation traffic. The programs can overlay air traffic with a wide selection of maps such as geopolitical boundaries, air traffic control center boundaries, high-altitude jet routes, satellite cloud and radar imagery. Problems, edit. Traffic, edit.